imagine just for a second shaving a few mere nanoseconds off a single computer task.
Right, something entirely invisible to you.
Exactly. It's completely invisible. But now, imagine that microscopic tweak compounding, like stacking up billions of times over.
Yeah, to the point where it saves a massive server architecture, literally hours of processing time.
Yes, allowing it to, chew through a 5,000 chapter text file without dropping a single frame.
It's wild to think about.
It really is. And today, we are hunting down that friction. Welcome to the deep dive. We have a highly specific mission today for you, and we're exploring the relentless, almost obsessive pursuit of systemic optimization.
Obsessive is definitely the right word for it.
Oh, totally. We are looking at how granular changes in the way we process data, whether that data is digital text, physical water, or like biological nutrients, can compound into massive real-world gains.
It's a profound shift in perspective. I mean, if you stop looking at systems, any systems really, as static environments.
Right.
And you start looking at them as malleable architectures. You realize that optimization isn't just about raw speed.
Right. It's not just making the engine run hotter.
Exactly. It's about elegant design. It's about systematically reducing the energy required to get a payload from point A to point B.
Essentially eliminating those bottlenecks that quietly strangle a system's capacity, right?
Spot on.
And the stack of sources we are analyzing today is honestly a masterclass in that exact mindset.
It really is a sprawling collection.
Oh, massive. What we are looking at is this incredibly diverse collection of technical logs and engineering project notes.
Covering everything.
Literally everything. Hyper-complex software engineering, home networking, and then it just extends into botanical propagation and fluid dynamics in fish tanks.
Which sounds completely disconnected, but it's not.
Not at all. We're going to focus entirely on the core of these experiments, the raw methodology of finding friction and engineering a way around it. But to ground this for you, we are going to anchor our conversation on one specific, beautifully detailed case study from these sources.
The Haskell parser.
Yes, tweaking a chapter parser written in the Haskell programming language. Okay, let's unpack this.
Let's do it.
The core technical problem detailed in these logs involves how this Haskell software searches for information within a string of text.
Right. Specifically, this parser needs to identify certain characters, delimiters, within a massive body of text, just to separate it into chapters.
Like finding the chapter breaks in a huge novel.
Exactly. And the focal point of the optimization here was a fundamental shift in the underlying data structure used for that search operation.
Okay, so what did they actually change?
Well, the logs detail a shift from using a standard string-based list check, which is essentially just an array, to using a mathematical set.
Okay, and for anyone who, has taken a computer science class, the theoretical reasoning here is classic algorithmic scaling.
Right, the classic big O notation.
Exactly. The notes explicitly state this is a move from O of n time complexity to O of log n.
Yeah.
Now, we all know big O notation is just a way of expressing the worst case scenario for how an algorithm scales as the data set gets bigger.
Right, as the input grows.
But the mechanism of why it scales differently is what really matters here, I think.
Precisely. Because in a standard list, an O of n structure, the search time grows linearly.
So 1 to 1.
Right. If you are searching for a specific character, the algorithm starts at index 0 and checks every single item sequentially.
It's just going down the line.
Yeah, so if your data set has 1 million items, a worst-case search requires 1 million discrete operations.
Okay, so to visualize the mechanism here, let's think about this like, let's use a grocery analogy.
I like that.
So an O of n list search is the equivalent of looking for a specific ingredient by checking every single item in your grocery bag one by one.
You pull out the apples, nope. You pull out the bread, nope.
Exactly. It's just brute force. You check every single thing until you find the paprika.
Which is terribly inefficient if you have a lot of groceries.
Right. But moving to a set, which in Haskell is typically implemented under the hood as a highly balanced binary search tree, gives you that O of log n efficiency.
Right.
So that is like using a perfectly categorized pantry where you instantly narrow down the location.
You know the paprika's in the spice rack.
Exactly. You just eliminated 90% of your search space in one decision. Then you look at the savory spices and you have it again.
It's a brilliant way to conceptualize the algorithmic halving.
Yeah.
Every single step in an O of log n operation drastically cuts down the remaining data set.
So much faster.
Oh, infinitely.
Hmm.
Even if you scale that grocery bag up to 1 billion items, it might only take 30 operations to find your target in a set, rather than 1 billion in a list.
So the theoretical superiority of a set over a list for lookups is undeniable.
Absolutely undeniable.
But here's where I want to push back a little bit.
Oh,
Because theory is great on a whiteboard, right? But practical compilation is messy.
oh, it is extremely messy.
In Haskell, or really any language, data structures aren't free. Building that highly balanced binary search tree, sorting the data into a set in the first place, carries its own overhead.
Yes, the O of n log n construction cost.
Exactly. Plus, you have, like, pointer overhead and memory allocation.
Right, there's always a tax.
So if your chapter parser is only ever checking against a tiny list of 3 or 4 delimiter characters, the overhead of building that set might actually be slower than just doing a brute force scan of a tiny array.
That's a very fair point.
Right. So theory is great, but does this math actually hold up when the code hits the compiler?
This raises an important question, and it is the crux of why these project logs are so valuable.
Because they actually tested it.
Exactly. The methodology doesn't stop at theoretical assumptions. There is almost always a gap between computational theory and hardware reality.
Oh, totally. Things like branch prediction or CPU cache misses.
Garbage collection, yeah.
Yeah.
All of that can completely invert your expectations.
So what did the author do?
Well, the engineering notes acknowledge this exact potential overhead. So to prove that the O of log n scaling actually outpaced the overhead of the set structure in this specific use case, a rigorous benchmark test had to be implemented.
And the tooling used here is what makes the data so reliable, I think.
The criteria library, yeah.
Yeah. The logs detail tasking in AI to generate a highly specific benchmark script using the Haskell criterion library.
Which is fantastic.
And for context, criterion isn't just like a simple stopwatch timer.
No, it's an industry-standard profiling tool.
Right. It runs the code thousands of times, performs statistical regression, isolates kernel density estimates, all that good stuff.
It effectively strips out the background noise of the operating system to give you pure execution metrics.
Okay, so the AI generated this benchmark. How was it structured?
The structure was exceptionally methodical. It didn't just test a generic search. It isolated 3 distinct states of the parsing operation to see exactly where the data structures diverged.
Okay, what was the first one?
First, it tested the best-case scenario, where the parser is looking for a character and finds it on the very first check.
So sticking with our analogy, that's the equivalent of opening the pantry, and the paprika is literally the very first thing at eye level.
Exactly. Immediate success. Then, it tested the worst-case scenario.
Okay.
The parser is forced to search through the entire structure, only finding the target character at the absolute last position.
The very back of the bottom shelf.
Right. And the third scenario, which the logs heavily emphasize, is the not found case.
Ah.
The parser scans the entire structure and confirms that the target character simply does not exist in the dataset at all.
We really need to pause and analyze that third scenario, I think.
Oh, definitely. From a systems architecture standpoint, the not found state, the failure state, is frequently the most critical bottleneck in an application.
Which feels incredibly counterintuitive at first.
It does, yeah.
Until you look at how digital logic gates actually operate. Think about your own tech stacks, or even the database queries you write. We always optimize for the happy path.
Right, assuming the data is actually there.
Exactly. But to definitively prove a negative to confirm something is not there. A basic O of endless search has no choice but to exhaust every single possibility.
It cannot short circuit. It cannot stop early.
It has to check every single item to be absolutely sure.
And if your system is processing dirty data, handling user typos, or constantly validating against missing elements, it's spending an immense amount of computational energy just confirming negative.
Just spinning its wheels.
Precisely. A slow, not found response acts as a silent anchor, just dragging your application's throughput down.
So optimizing a system's ability to confidently fail fast is a massive performance unlock.
It's huge.
Okay, so we have the binary tree mechanics, we have the criterion profiling environment, and we have isolated these critical failure states. I was looking at the graphs generated in these logs, and the hard data is honestly staggering.
The quantitative results validate the architectural shift perfectly.
Okay, lay the numbers on us.
So in the best case scenario, the set structure outperformed the lift by roughly 24%.
Which is great. That alone is a solid win, easily justifying the overhead of building the set.
Exactly. But in the worst case scenario, and in that incredibly crucial not found scenario, the performance jump was a massive 63%.
Wow, 63%.
A 63% reduction in latency on your most computationally expensive operations.
That is insane. I mean, in software engineering, you usually fight tooth and nail for like a 3 or 4% optimization.
Oh, absolutely. 63% fundamentally changes the capacity of the software.
And what struck me wasn't just that top speed, but the latency distribution.
Inconsistency.
Yeah. The logs included the HTML output graphs generated by Criterion. And if you look at the bottom 3 graphs tracking the set's performance, the variance is practically non-existent.
It's so clean.
It isn't a jagged line of spikes and dips. It is a flat, predictable line.
Which is often way more valuable than raw speed.
Really? Why is that?
Because predictable execution times, minimizing tail latency, means you can scale your system architecture horizontally with actual confidence.
Oh,
You don't have to worry about random processing spikes triggering timeouts in other parts of your application.
Okay, so what does this all mean? We're talking about a 63% improvement, but the logs make it very clear we are measuring these operations in mere nanoseconds.
1/1000th of a second.
Literally a billionth of a second. Why go through all this trouble? Why dedicate this level of extreme engineering, profiling, and restructuring just to shave a few billionths of a second off a text search?
If we connect this to the bigger picture, the answer lies in the sheer volume of operations.
Okay.
A single nanosecond is imperceptible, obviously, but software operates in loops. This parser wasn't built to read a single paragraph. The logs explicitly mention that this architecture is designed to parse text files containing thousands of chapters, specifically noting that some web novels have over 5,000 chapters.
That is a massive amount of text. So if you are executing a search operation on every single line, looking for delimiters across millions of lines of text.
You are executing that logic millions, potentially billions of times.
Right.
A 63% improvement, compounded a billion times over, scales exponentially.
It adds up fast.
Nanoseconds become milliseconds, milliseconds become seconds, and suddenly you are saving minutes or even hours of continuous CPU cycles.
Wow.
But the logs introduce an even more critical architectural detail here.
What's that?
The system is converting multiple text files asynchronously.
Oh. Right, running concurrently in a thread pool rather than just waiting in a sequential queue.
Exactly.
Yeah.
And when you introduce asynchronous concurrency, the slow components of your code base create cascading bottlenecks.
Because they hold up the line.
Right. In a language like Haskell, which relies heavily on lightweight green threads managed by a runtime scheduler, if one thread gets blocked executing a slow, brute force O of n not found search,
It occupies computational resources.
it holds on to memory. It starves the thread pool.
It basically creates a massive traffic jam at the CPU level.
Exactly. By optimizing that core parsing action at the microscopic level, you aren't just speeding up one isolated task.
You are dramatically increasing the throughput of the entire asynchronous architecture.
You free up the thread pool. It allows the server to process massive 5,000 chapter payloads concurrently without memory exhaustion or CPU blocking.
It's basically the butterfly effect applied to server architecture.
That's a great way to put it.
A microscopic algorithmic tweak in a data structure ripples outward, preventing a massive asynchronous queue from just collapsing under its own weight.
It is deeply satisfying to see the theoretical math translate so flawlessly into real-world scaling.
It really is a perfect closed loop of hypothesis, testing, and validation. But, the most compelling aspect of these project logs isn't actually limited to Haskell profiling.
No, not at all.
It's the fact that this specific engineering mindset, observing a complex system, identifying the point of friction, and methodically engineering a smoother path, is applied across completely disparate domains in these notes.
What's fascinating here is the universality of the methodology.
Here's where it gets really interesting, because the digital optimizations are just the beginning.
Right.
The logs transition from software engineering directly into biological and physical systems, applying the exact same framework.
It's incredible. Let's look at the gardening and botanical propagation notes.
Yes. The author isn't just, watering plants. They are testing nutrient delivery mechanisms.
They are experimenting with bottom watering, for instance.
Right. To manipulate capillary action in the soil, forcing the roots to grow deeper.
And they are isolating variables by using single node cuttings for propagation.
Which effectively minimizes the biological energy the plant wastes on sustaining unnecessary foliage while it tries to root.
Right. Exactly. They are optimizing the biological energy budget. But I think the most striking parallel is the introduction of mycorrhizal fungi to the soil.
Oh, yes. The logs detail testing mycorrhizal fungi to boost plant health. And if you think about how that works biologically, it is practically identical to the O of log n optimization we just discussed with the set structure.
It really is. A
Yeah.
plant's standard root system is essentially an O of N list search.
Explain that.
Well, the root has to physically push through the soil, millimeter by millimeter, searching for water and phosphorus.
Right. Checking every single bit of dirt.
It's slow, it's linear, and it's highly energy intensive.
But when you introduce mycorrhizal fungi, the fungi attach to the roots and create this massive subterranean mycelial network.
It acts as a biological set structure.
Exactly. The fungus effectively acts as an API, extending the plant's search space exponentially.
The plant no longer has to linearly search the soil.
Right. It just plugs into a highly indexed fungal network that delivers nutrients directly,
Drastically reducing the latency of the plant's growth cycle.
without requiring the plant to expend all that linear energy.
It is a stunning biological equivalent to a distributed cache or a search tree.
It blew my mind.
And the logs don't stop at botany. The application of this optimization framework to fluid dynamics and aquatic ecosystems in the fish-keeping notes is equally rigorous.
Oh, the aquarium notes read like civil engineering logs.
They really do.
They're detailing the use of specific three-way PVC pipes to alter the flow dynamics of the tanks,
They are intentionally disrupting laminar flow to create turbulence,
specifically to eliminate dead spots where detritus builds up.
which is an optimization of the nitrogen cycle, ultimately.
Right.
By engineering the fluid dynamics to ensure continuous movement, they're maximizing the efficiency of the biological filtration.
Ensuring the beneficial bacteria can process ammonia at peak capacity.
Exactly.
And then there are the behavioral optimizations, which were wild to read about.
Oh, the monsoon simulations?
Yes. The logs detail simulating monsoons by doing massive cooler water changes to trigger barometric and temperature shifts in the tank.
They are literally hacking the biological state machines of the fish to trigger breeding cycles.
It's unbelievable. Or look at the notes on the golden Mabuna tanks.
Right. African cichlids, they are notoriously aggressive.
Super aggressive. And the logs detail tweaking the rock formations and sight lines to break up territories.
Effectively optimizing the social hierarchy to minimize the friction of aggression.
They are mitigating behavioral bottlenecks.
Exactly. Whether it's the physical fluid dynamics or the social dynamics of the Mabuna, they are actively engineering the environment.
It's all connected.
It is. There are even logs analyzing the radio frequency spectrum, optimizing home networking by tweaking Wi-Fi 7 configurations on a MediaTek MT7925 chip.
All to minimize packet loss and connection latency.
We have a tendency to compartmentalize our disciplines.
Oh, totally. We treat computer science, botany, fluid dynamics, and radio frequencies as isolated fields.
But these project notes demonstrate that the framework of improvement is entirely agnostic to the medium.
The medium changes, but the algorithm of optimization remains exactly the same.
Precisely. You observe a complex system. You identify the bottleneck, whether that's the O of N brute force search, the laminar flow dead spot, or the unrooted plant cutting wasting energy.
Right.
You implement a structural change to bypass that friction. And then you measure the compounding results over time.
It's universal.
Whether you are dealing in nanoseconds of CPU time or weeks of botanical growth, the drive to build a more elegant, efficient system is a fundamental human pursuit.
It really is a powerful lens through which to view the world around us.
Well, we have covered a massive amount of conceptual ground today.
We really have.
We started at the absolute microscopic scale, profiling nanoseconds within a Haskell compiler, explored the compounding mechanics of asynchronous server architecture.
And zoomed all the way out to the biological networks beneath the soil and the fluid dynamics of aquatic ecosystems. I hope this deep dive has shown you how a simple, methodical upgrade, like swapping a list for a set to gain a 63% efficiency boost, can fundamentally alter the carrying capacity of the systems we build.
It definitely forces you to appreciate the invisible, optimized architecture that quietly supports our daily lives.
It really does.
But if I can leave you with one final thought to explore on your own.
Please do.
Considering how drastically a microscopic inefficiency compounds when a server processes a 5,000-chapter text file, it's worth auditing your own routines.
Ooh.
What mental or digital lists are you still relying on that really need to be upgraded to sets?
That's a great point.
If you could re-architect the way you search for, process, and store your everyday information, whether that's your email inbox, your file directories, or just your daily workflow, how much compounded asynchronous time could you win back for yourself?
Now, that is a question worth sitting with the next time you find yourself doing a brute force search for a missing file. Thank you so much for joining us on this deep dive today. Keep questioning the friction in your own systems and keep optimizing. We will catch you next time.